Most beginners pick the wrong compute service and hemorrhage cash. But what if you could use spare cloud capacity sold at deep discounts? That's exactly what spot VMs are, preemptible VMs that Google can terminate with only a short warning. Get this decision wrong and you wake up to a 3 a.m. outage. Get it right and you slash your compute bill dramatically. In this video, you'll learn the exact decision tree to stop paying for idle time and sleep through the night. You're watching Part 3 of the GCP Fundamentals Study Guide. In Part 2, we covered global infrastructure and networking, how GCP's private backbone gives you lower latency and rock-solid connections. Now we shift to compute, the engine that actually runs your code. By the end of this video, you'll know exactly which of the 5 core services, Compute Engine, GKE, Cloud Run, App Engine, or Cloud Functions, to use for every workload you'll ever touch. Every compute decision is a trade-off between control and ease of use. On the left, Compute Engine gives you full control over the VM. You're the landlord managing the whole building. On the right, Cloud Functions handles everything. You just drop in code. In between, you have Google Kubernetes Engine, GKE, which is Google's fully managed Kubernetes service. Kubernetes is the open-source platform that orchestrates containers. Then you have serverless containers with Cloud Run and the fully managed web platform App Engine. Keep this spectrum in your pocket. You'll reference it on every project. Here's a common mistake. A startup chose GKE for their simple API because it sounded powerful. They ended up paying for an idle node and spending time on cluster maintenance. Meanwhile, another startup running the same app on Cloud Run paid almost nothing when traffic was low because Cloud Run scales to 0. The lesson? Match the service to your actual workload. Don't just default to the most powerful option. Compute Engine gives you a full virtual server, a virtual machine with its own operating system, kernel, and root access. Think of it like renting an entire apartment instead of a room in a managed hotel. You own the OS, you install the patches, you configure the firewall, and you lock the doors. In return, you get total control. It's the IaaS workhorse, the foundation for lift and shift migrations, custom Windows Server images, or anything requiring a specific kernel version. You asked for the keys, now you're the sysadmin. Compute Engine offers a range of machine types tailored to different workloads. General-purpose VMs balance cost and performance for everyday web servers. Compute-optimized VMs deliver more CPU per core for demanding tasks. Memory-optimized VMs crank up the RAM for in-memory databases. Accelerator-optimized VMs let you attach GPUs for machine learning. And storage-optimized VMs provide fast local SSDs for analytics. The key: match the machine type to the workload and you'll avoid overpaying. Quick recall. Which VM family type delivers the highest per-core CPU performance for CPU-bound workloads? Pause and think. The hidden money-saving feature most beginners ignore: custom machine types. Instead of using a fixed shape like N1 Standard 2, which gives you 2 vCPUs and 7.5 GB of memory, you can specify exactly what you need, say 1 vCPU and 3.75 GB of RAM. That can substantially reduce your bill because you're not paying for resources you don't need. The common mistake is never checking if a custom type fits better. Make it a reflex. Before you launch a VM, ask yourself, can I downsize with a custom shape? But here's the part almost everyone gets wrong. Spot VMs can slash your bill by a huge margin. Discounts often hit 60 to 91% compared to on-demand. A batch workload that normally costs $500 might run for as little as $50 with spot pricing. The catch? Google can terminate your VM with only a short notice the moment it needs the capacity back. That's perfect for fault-tolerant batch jobs, rendering, or genomics. It's a disaster for a production web server that can't afford a surprise reboot. Use spot VMs, but only for workloads that can handle the interruption. Otherwise, you'll be the one answering the 3 a.m. call. Compute Engine isn't just raw VMs. 4 built-in capabilities make it a production-ready power tool. Live migration keeps your apps running through physical maintenance without a reboot. Persistent disks let you keep data even after you delete the VM. Managed instance groups handle auto-scaling, auto-healing, and zero-downtime updates. And startup scripts automate your initial OS configuration the moment the VM boots. Together, they let you run a self-healing, auto-scaling web farm without ever touching the console. Here's exactly how a managed instance group keeps your app alive. A load balancer sends user requests to the group. The MIG acts like a supervisor, constantly monitoring VMs with health checks. When a VM fails, marked with a red X here, the MIG automatically terminates it and provisions a brand new healthy instance. Meanwhile, if traffic spikes, the MIG auto-scales by spinning up additional VMs on the fly. No manual intervention. That's high availability on autopilot. Let's actually spin up a VM in the Google Cloud Console. After opening Compute Engine, you create a new instance, name it Web Server 1, and pick zone US Central 1A. The E2 medium machine type gives you 2 vCPUs and 4 GB of RAM, plenty for a web server. Choose a Debian 11 boot disk and enable the firewall option to allow HTTP traffic so the console automatically creates a rule for port 80. Hit Create, and in under a minute you have a live Linux server in the cloud. For infrastructure as code or just speed, here's the G-Cloud equivalent. The Create command provisions an E2 medium VM with Debian 11. The E-tags flag is a sleeper hit. It marks the instance as an HTTP server, so the subsequent firewall rule allows TCP port 80 only to VMs with that tag. After that, you can SSH directly into the machine and install Apache with a single apt-get line. In less than 5 minutes from cold start to serving web pages. Time to lock in what you've learned. First, spot VMs. They can save you up to 91% over on-demand prices, perfect for batch jobs that can tolerate interruption. Second, recall our Part 1 G-Cloud quiz. How do you check your currently active project? If you're unsure, flip back to Part 1. Those fundamentals are the backbone of every command you'll run. Here's the mistake that kills most container projects before they start. Assuming it worked on my laptop. Guarantees production success. Containers are like steel shipping containers for your application. They bundle the code with every library, runtime, and configuration file it needs, so it runs identically everywhere. Your laptop, a test cluster, or a Google data center. Once you adopt containers, the phrase "works on my machine" disappears from your vocabulary. But when you start running dozens or hundreds of containers, you need an orchestrator to keep order. That's where Kubernetes comes in. Kubernetes itself is a beast. It's a distributed system that schedules containers across machines, handles failures, and scales. The brain of the whole thing is the control plane. 4 core components. The API server is how you and every other tool talk to the cluster. The scheduler decides which node gets each new pod. The controller manager runs controllers that continuously drive the cluster toward the desired state. and etcd is the cluster's memory, a key value store that holds the entire desired state. With GKE Standard, you manage the worker nodes, the VMs that actually run your containers. With Autopilot mode, Google manages the nodes for you. You don't provision or maintain them, though they're still visible in your project. You only define your workloads, and the smallest deployable unit is a pod. A pod wraps one or more containers that share network and storage, and it's the atomic unit of scheduling. If Kubernetes were a restaurant, pods are the plates of food, the control plane is the kitchen manager, and GKE Autopilot is the fully staffed restaurant where you just order off the menu. The big fork in the road with GKE is Standard versus Autopilot. Standard gives you full control. You choose the node type, you manage upgrades. But you pay for every node even if it's sitting there doing nothing. Autopilot flips the model. Google runs the cluster infrastructure behind a curtain. You only specify pods, and you're billed based on the resources your pods request. And with proper configuration, your workloads can scale down when idle, potentially lowering your bill significantly. For most new workloads, especially API services, Autopilot saves you money and management headaches. Let's pull the curtain back on a GKE cluster. Traffic enters through a cloud load balancer and hits an ingress resource, which routes requests based on URL paths or host names. The ingress forwards to a Kubernetes service, a stable virtual IP that abstracts away the ever-changing pod IPs. The service sends work to a deployment, which acts like a foreman. It keeps a desired number of identical pods running, replacing any that die. Those pods are spread across the physical nodes in the node pool. The key takeaway: the pod is the atomic unit of scheduling. Everything else, deployments, services, ingress, exists to manage and expose pods. Let's get a container live with 4 commands. eCloud container clusters, create auto, spins up a fully managed GKE Autopilot cluster. No nodes to configure. Then, get credentials, wires your local kubectl to the cluster. The magic starts with kubectl create deployment. It pulls the Hello App container image from Google Container Registry and launches a single pod. To make the app accessible from the internet, kubectl expose with type soch and load balancer attaches an external IP and opens port 8080. Wait about a minute, run kubectl get service, and you'll have a public IP, your containerized app, served by Google's planet-scale infrastructure. Let's cement 2 concepts. First, pods. A pod holds one or more tightly coupled containers and is the smallest thing Kubernetes schedules. You never ask Kubernetes to schedule a single container, it always wraps it in a pod. Second, recall our Part 2 question. How does an edge location differ from a region? If that tripped you up, revisit Part 2's Network Architecture chapter. The details matter when you're designing global applications. Cloud Run is fully managed serverless containers. When there's no traffic, it scales to 0, meaning you pay nothing. The instant a request hits, it spins up an instance in milliseconds, processes it, and you're only billed for the CPU and memory consumed during that request. The punchline: you pay per request, not per server. No idle bills hiding in your cloud account. Cloud Run and GKE both run containers, but they serve very different masters. Cloud Run is the I just want my container to run and scale to 0 path. Fully managed, zero-effort serverless. GKE is Kubernetes, the enterprise standard. You get the full control plane and all the networking complexity, but you're also babysitting nodes. A good rule of thumb: APIs and stateless microservices love Cloud Run. Stateful apps and teams that already live in Kubectl love GKE. Deploying to Cloud Run is a single gcloud command. The two flags you need to care about: platform managed tells Google to handle everything serverlessly. No cluster headaches. Allow unauthenticated opens the service to the internet, which is great for a public API, but a terrible idea for internal tools if you forget to lock it down later. After a few seconds, you get a URL. Your app is live, scaling to 0 when the traffic stops. App Engine, Google's platform as a service, comes in two flavors. Standard environment. You push code. Google handles scaling and infrastructure. Flexible environment. Your app runs in a container on dedicated virtual machines, giving you more control and persistent background processes. Think standard like a hot water tap that only fires up when you need it. Flexible is the always-on espresso machine. The standout difference: standard can nap. It scales to 0, so a low-traffic dev site costs pennies. Flexible stays awake even when nobody's watching, which is why it's used for long-running background workers or legacy apps that need a specific OS. If you're building a modern web API that should react quickly and stop charging you when idle, standard is almost always the right call. Let's lock in the App Engine distinction. Pause and recall. What's the core difference between standard and flexible? Standard abstracts everything away, scaling automatically. Flexible gives you a VM you can control. Knowing this will guide every future deployment decision. Cloud Functions is the ultimate fire-and-forget compute. You write a tiny piece of code, and it runs only when an event happens. An HTTP call, a new file in a bucket, a pub sub message. There are no servers to manage, and you pay only for execution time. That's event-driven, zero-server, pay-per-execution compute. It's perfect for webhook handlers, light ETL, or image thumbnailing. Here's a real cloud function triggered by pub esyam sub. The function's Socher framework. Cloud event decorator routes incoming events. When using the Cloud Functions framework, the message payload is automatically decoded from base 64 for you. However, if you're working with raw pub sub-events, you'd need to decode it manually. We'll show the explicit decode step here for completeness. This is event-driven compute in its purest form. No servers, no polling, just a function that fires when needed. Cloud Functions. Second Gen is a huge upgrade. It's built on Cloud Run under the hood, which means you get a much longer timeout, concurrency support so one instance can handle multiple requests, and bigger memory limits. The most common pitfall: developers use first gen for a job that runs long, and it gets cut off because first gen has a short execution limit. If your workload needs extended execution, switch to second gen. It's literally the fix. Your stuff won't time out because the server got bored. When you're staring at the GCP console, here's the compute decision tree that will save you. Start by asking, is the workload containerized? If yes, and you need full Kubernetes magic, stateful sets, network policies, go GKE. If it's a stateless API that should scale to 0, Cloud Run is the winner. If no containers, ask if you need full OS control. That's compute engine territory. Otherwise, web apps belong to App Engine, and event-driven glue belongs to Cloud Functions. Follow this tree and you'll rarely pick wrong. All right, let's actually use the decision tree. First example, you need a static company website. Maybe a brochure site with almost no traffic. Is that workload containerized? Nope. Do you need full OS control? Not at all. You just want to serve some HTML. So the tree says App Engine Standard. Why? Because it's a fully managed web platform, it scales automatically. And for extremely low traffic, it can fit within the free tier's generous quotas. Your bill could be zero. But if traffic spikes, you'll start paying for usage above the free tier. Second example, a containerized REST API that sees variable load, idle most of the night, but spikes during business hours. Since it's containerized and stateless, the tree asks, need Kubernetes complexity? No, it's just request-driven. That lands on Cloud Run. Perfect fit. Scales to zero, request-based billing, and zero infrastructure ops. That's the pattern. Stay on the left when you want control. Slide right when you want hands-off. Checkpoint. Let's lock in that cost data. Which service wins on monthly spend for a low-traffic app? Pause and recall. Quick check. You need to run a stateless containerized app that scales to zero and only charges per request. Which GCP service fits best? Here's your cheat sheet for picking the right GCP compute service. For full OS control, go with Compute Engine. Need complex Kubernetes? That's GKE, containerized API that's stateless and request-driven. Cloud Run. Traditional web apps? App Engine. Event-driven glue code. Cloud Functions. Screenshot this right now. It'll save you hours of second-guessing later. That's the compute spectrum on GCP, from raw virtual machines all the way to tiny event-driven functions. One more power tip. Spot VMs can cut costs by up to 91% on batch and fault-tolerant workloads, a massive saving when you don't need guaranteed uptime. Next up in Part 4, storage options. Where your data lives. We'll cover cloud storage, persistent disk, and managed databases, and how to pick the right one. Hit subscribe so you don't miss it.